name is Ankur and I am here to present a new network inspection tool called FlowInspect. FlowInspect is basically a Python-based POC implementation. It is a network inspection tool. It can actually detect network streams in various modes. It has a number of ways in which you can actually detect for malware or presence of shellcode. There are a number of other features in it. And I'll be talking about the architecture of the tool. I will be talking about the CLI usage. I'll be showing some real-world demos as well. First of all, let's have a look at the outline of the talk. We'll be starting with the incident response requirements. Actually, whenever a new threat incident pops up, how exactly would you address that particular incident? What tools will you use? And what are the missing features that the current solution, the current tools have? With those missing features, we will try to visualize what are the features that should be present in an ideal inspection tool. Once we have those, once we have that vision and the design goals noted down, I will try to introduce FlowInspect as a viable solution. FlowInspect will try to address those missing gaps as much as possible. I'll talk about its architecture, CLI usage and examples. We will have a look at some real-world demos as well. And finally, we conclude with future goals. What new features have to be added? So for the first point, understanding the incident response requirement. So consider this scenario. You read about a new threat incident, and someone calls you up and says, "Hey, I have something bad happening in my network. Please come down and have a look." You pile up your tools. You reach the place. You investigate the incident, and you finally find some traces of a malware. Now, once you have this particular information, you would like to know what exactly happened there. What were the actors involved? By actors, I mean what were the exact hosts? Who was the attacker? How many victims were targeted? And what exact information did they share? Was it secretive? Was it confidential in any way? Or what other hosts were compromised? Once a target was compromised, how many other hosts were compromised using that as proxy? So these are some details. So basically, you are looking for some data, and we are talking about network data. We are talking about the vulnerability or the exploit that was used to actually launch the target, the CNC communication that happened between the two hosts or the multiple hosts, between the attacker and the victim, basically. And to do all this, you have a few open source, and there are also a few commercial solutions as well. Primarily, we will be looking at Wireshark, TCPDump, ngrep, and FlowGrep because they are open source. I have been using them for a number of other requirements, and most of you here might have used these tools. If not all of them, a few of them. And the problem here is these tools, they were designed to address a very specific requirement, or they have a very specific feature set. For example, these tools, they all share a few shortcomings. They are basically stream or flow agnostic. They don't know what is happening on the L7. They don't have the L7 or the stream details with them. And also they lack many new to detect latest threats, you need some inspection features that are missing from these tools. Basically what I'm talking about is, for example, TCPDump and Wireshark. These two tools, they were designed to be packet sniffers, basically. Wireshark also has an awesome protocol decoding feature in it. It can decode a number of protocols, abstract protocols, but primarily it is a network, it is a packet sniffer and a protocol decoder. So there are not many network inspection features built into it. Talking about ngrep and FlowGrep, I don't know how many of you here have used ngrep. If you can, by the raise of a hand, tell me how many of you here have used ngrep. Anyone? No? Okay, just one guy. He's from Juniper. So people in the network industry might have used ngrep. ngrep is basically a tool that you can use. It is a packet sniffer. At the same time, it accepts a regular expression. It matches that over the TCP or the L4 content. If a match is found, it turns that match on the screen, whatever the output options were specified. The problem with ngrep is that it would match a regular expression on individual packets payload. So I mean, if there are a number of TCP packets coming, regular expression would be matched on the payload of individual packets. If a match is found, it will be shown, and if a match is not found, the packet content would be dumped. And in that case, this inspection would move on to two subsequent packets. So if in case you are trying to look for some data that spans multiple packets, ngrep won't be able to find a match in that case, because data is spanned across multiple packets and inspection is happening on a per packet basis. Okay. Now here is where FlowGrep comes into picture. FlowGrep is a tool that can actually extract TCP streams out of network packets. It can then use the regular expression, match that over the TCP, reassemble TCP stream. Now the problem with FlowGrep is that it cannot do shellcode detection on the wire. So FlowGrep can match regular expressions on network data, but since it is a POC tool, there are no features to detect shellcodes and malware in FlowGrep. So basically, these tools, they lack some of these features, and this actually, made me realize that there are a number of other features that are missing from current network inspection tools, and I would like to have these features and many more other features to be present in an ideal network inspection tool. I noted these points down, and basically I noted the feature set for an ideal inspection tool. What exactly should be present? What features or what benefits should I have while using a ideal inspection tool? The first point that I had in my mind was it should be able to identify malwares. There are a number of techniques you can identify malwares with. At least signature-based malware identification should be one of them. So there are a number of other techniques like you can use anomaly or behavioral-based malware detection. You can use sandboxing techniques. You can use binding instrumentation techniques, static or dynamic analysis. But at the very minimal, signature-based detection should be a feature that should be present in such a tool, an ideal network inspection tool. The second point would be shellcode emulation. So I mean a network inspection tool should be able to tell me if a particular network stream has shellcode embedded into it. If there is shellcode, if shellcode is on the wire, the tool should be able to identify it and let me know if there is some shellcode or certain kind of shellcode, some binary opcodes being transferred from a host A to a host B. Then there should be a facility of extracting matching flows out of network streams and dumping them to a file. Now this would help if in case you identify a malware and you would like to keep a copy of the malware as well. So identifying alone is not enough, you would also like to keep a copy of the malware as well. So a tool should also have extraction facility. So it should not blindly inspect and then discard the data, it should also keep a copy. Then there should be some match statistics, like if a match happened, if you find a malware, but on what particular direction the match happened, whether the match happened on the traffic that was moving from the client towards the server or from the response that was coming from the server towards the client. So this would actually help me to identify what kind of exploit was used. Was it a client-side or a server-side exploit? So these are some details that should be present in an ideal inspection tool. There should be some snort-like content modifiers, like if you have a 100 byte buffer and you would like to match only, you would like to start matching at the 10th offset because you don't really care about the first 10 bytes. You don't want to match them. So you should have a feature that actually lets you to specify custom inspection offset. So match should start at offset 10, and if you would like to inspect only next 20 bytes, so you should have a feature called depth. So using a feature called depth, you can actually specify how deep inside a particular flow you would like to inspect. So starting at offset X, you want to inspect till offset Y, even though the size of the entire buffer is higher than X and Y. There should be PCAP generation facilities as well, so that you can actually keep a trace of the entire network activity. And if required, if you find a malware, for example, and you would like to block that particular, you would like to stop that particular connection, you should have a TCP reset or TCP fin injection facility as well. Like most of the network intrusion prevention systems, what they do is, as soon as they find a match, they will drop the connection. So such a feature should also be there. If you find a malware infection, you should be able to drop it. So with this vision and with these design goals in mind, I started working on a tool. I came up with FlowInspect. Here it is. It is a Python 2.7 implementation. It is a POC tool. It has a number of modules, primarily 3: input, inspection, and output. Input module would take network traffic in. It can take network traffic in either through a PCAP file or through live network interfaces. Once the traffic is in, it will extract streams out of TCP packets, and once you have TCP streams, the buffers are populated, and then whatever inspection mode you have selected, based on those CLI options, inspection would happen. Once inspection happens, if a match is found, depending on the output modes, output would be dumped either to a file or to a PCAP or to stdout. Alright. FlowInspect also supports IP defragmentation and TCP reassembly. So I mean, If you see TCP packets, if FlowInspect sees TCP packets, it will actually reassemble the TCP packets and extract streams out of it. So there is no individual per packet basis inspection here. So if you have used Wireshark, there is a, whenever you open a TCP PCAP in Wireshark and you right click on it, you have a option for following a particular stream. So once you follow a stream, you see the entire content, CTS and STC data, the red and the blue part. So that is particularly highlighted. Everything is reassembled, and this is the entire buffer that the L7 application sees. So if you are opening up a web browser, even though Wireshark shows you individual packets, the browser will actually see this reassembled buffer. Okay, this is the entire page that the browser sees, and it will actually act upon it. So this is the buffer that you are interested in. You would like to inspect this buffer, because this is what the actual application is working upon. So FlowInspect will actually take network traffic as input and give you that buffer. The input module will pass this buffer to the inspection module, and the inspection module will operate on that. Once you have this buffer, you can inspect it in a number of ways. Currently, FlowInspect supports 4 inspection modes. They are namely regex, fuzzy string matching, Yara. Yara is a malware identification classification tool, so there is Yara integration as well, and shellcode detection as well. So these are the 4 primary modes. There are a number of other modes planned in future releases. Inspection happens on individual, like I said, it happens on individual L4 packet contains reassembled data. So L4 packets would be, data would be extracted out of TCP packets, reassembled, and a buffer would be created. This will happen only for TCP packets. UDP inspection happens on a per packet basis. So in UDP you don't have a concept of client and server. So basically everything is on a per packet basis. So it will identify the flow, but it will inspect data on a per packet basis. And once the match happens, it will dump the matching flows depending on the output modes that you have selected. So there are a number of output modes. If you would like to see the data on STD out, you can dump it on STD out. There are a number of options for that. If you would like to dump the matching flows to a file, you can do that. If you would like to generate a PCAP file, you can do that. So these are the combinations. You can use them all together. You can create your own combinations of output modes as well. Okay, let's have a look at the architecture of FlowInspect. Input module basically uses libnids. This is a library that uses Linux kernel 20x, Linux kernel's TCP IP stack implementation, 20x kernel's stack implementation. So it actually allows FlowInspect to extract streams out of TCP packets. So the reassembly and the defragmentation part is taken care by the libnids. Libnids has a Python wrapper, PyLibnids, and I am using that to extract streams out of TCP packets here. It also accepts BPF expressions. BPFs are Berkeley packet filters. If you have used Wireshark, you can actually filter depending on a protocol or protocol field. So if you would like to only inspect TCP traffic, you can specify filter TCP. So all other traffic, all other protocol packets would be skipped. They would be ignored by the tool. So it has BPF expression support as well. Offset depth are supported, and you can actually specify a maximum number of streams or packets that you would like to inspect. So for a particular case, suppose if you are working on an issue and you would like to inspect only a certain number of packets or a stream, so you can use such counters, and there are CLI options. You can specify a random number of streams or packets to be inspected. So for example, if you would like to inspect only first 100 streams in the network or first 100 packets in the network, in that case you can use a CLI option and mention 100 to be the number of maximum packets that should be inspected. So after 100 packets, if no match was found, FlowInspect would stop at that point. Output match has these meta, print, hex, and raw. These are the output modes in which it can dump output to screen. Meta actually means it will show you the match statistics. Match statistics mean the direction of the match, size of the match, and what exact packet IDs are involved in the match. So if a match spans multiple packets, it will tell you, okay, this match actually happened on packet X and it spans up to packet Y. So 5 to 6 or 5 to 7, 5 to 9, that likewise. Hex and raw are obvious. Hex would dump matching data in hexagram format. Raw would dump it as is on the screen with binary characters. Print actually filters non-printable characters and prints only ASCII printable characters to screen. This is to inspect clear text or non-binary protocols like HTTP, for example. It has file writing and PCAP generation features like we already talked about. Let's now focus on individual inspection modes first of all. We will start with regex here. So this is a typical usage of how regular expression inspection mode can be used. I'm not sure if you can see this, but I will show you a demo. I have a pretty high font there, so you will be able to see it. But for now, just try to understand the concepts. Each of the inspection modes, except for shellcode, it is different. All three inspection modes, they have direction specific flags in them. So for regex, if you would like to inspect only CTS traffic that is moving from client to the server, or the requests that are moving from the client towards the server, you can use there are different flags for that. So CTS will have a different flag, STC will have a different flag, and if you would like to inspect both the directions, there is a third flag for that. So each of the inspection mode have 3 different flags for that. So in this particular case, I am using Flow Inspect to inspect, to test HTTP, clean HTTP PCAP, and I'm using the -c regular expression flag here, CLI option, and I'm passing a regular expression .star. Now .star is a expansive I mean it will match everything and nothing. If there is anything in the payload, it will match it. If there is nothing, it will still match. .star matches anything. So in this case, I'm just using it as an example. So in this particular PCAP, there is a CTS session, CTS request going towards the server, and there was a response coming back. So in this case, since I'm inspecting using the -c flag, only client to server traffic was inspected. And if you can see here, the get, download, whatever content you see in the hex dump output is what actually matched the .star expression. So on a PCAP, .star matched on CTS direction and data was dumped to STD out. Now this happened on a TCP flow, TCP stream. Match happened at STC direction, CTS direction. In the square brackets after CTS, you see the match offsets. So in the entire input buffer, match starts at offset 0 and it ends at a certain offset, 479 in this case. The size of the match is 479 bytes and it spans packet 1 and 1. That means it is contained entirely within packet 1. These are some of the details that are really helpful when you are working on, when you write signatures for, network issues, or when you are trying to detect network malwares and shellcodes. So we'll see some other examples as well. In the second line, you see down below, after the hex dump output, you see a UDP match happening. The second line here, it shows a UDP match. Match happened in CTS direction, obviously, because you have used -c flag. So matches will only CTS traffic would be inspected, and if matches are found, they would be done. So here, since there is no concept of flows, inspection is happening on a per packet basis. There is no range specified, like you have in the upper match. The match spanned packet 1 and 1. Here, the red box. It tells you that this particular match on TCP flow starts from packet 1, ends at packet 1. When in case of UDP, everything is on a single packet basis, so you don't actually see that output here. Alright, let's have another example. In this case, I'm using the -a flag, regular expression flag, using the same regular expression, but this time, if you see, for UDP we have STC matches as well, because here we are using -a direction flag. In this case, CTS traffic as well as STC traffic would be inspected. So in this example, the second hex dump output is from the CTS flow. The third hex dump output is from the STC flow. Here is an example in which I am trying to match a HTTP header called content type. Now HTTP hierarchy defines content type header to have capital C and capital T for content type. So in this case, I am using a regular expression, and by default regular expression matches are case sensitive. So in the first example, with this particular expression, the match failed. There was no match here. If you see the green box over here, matches, they show 0,0 for both UDP and TCP. In the second example, I am using another CLI option -i. I am disabling the case sensitive nature of PCRE by default, and now even though I am using a case, even though the input string is not exactly same, it will be matched in a case sensitive manner, and I find a match. Content type header of HTTP, we find a match over there. -b32 is one of the CLI flags. If you see in the top line, it actually allows you to filter how many bytes should be down to STD out. So if you have a huge number of bytes in a PCAP, and if the match size is like in MBs or in thousands, and you would only like to focus upon the first or starting few bytes, you can actually use this flag and tell it the number, -b and whatever number you need. So only that many bytes would be dumped to screen. So even though we have a match of like 1133 bytes in the second example here, only first 32 bytes are being dumped to the screen. So this is just for filtering the output content. Let's move towards the fuzzy string matching mode. Let me first of all talk a bit about fuzzy string matching. in normal string matching algorithms, what happens is the algorithm will actually try to look for exact matches of the input string. So if you are trying to match for a string HTTP in capital, it will try to look for the exact string capital HTTP in the same sequence, and if a match is found, it will actually dump it to the string. There are certain algorithms that look for exact matches, and they also support the case insensitive combinations of the input character. So in that case, HTTP case insensitive patterns would also be matched. But the basic concept here is that this is an exact match. HTTP exact string should be matched, and the character, the occurrence of characters should be fixed. H, then T, again T, and P. All these characters should follow each other in the particular sequence. Now, in case of fuzzy string matching, what happens is you don't actually look for exact matches; you look for relative matches. So, if in case of fuzzy string matching, there is a match percentage. So, even if a string is not 100% similar to the input string, it will tell you, the algorithm will tell you a certain percentage that this particular input string matches the input buffer, certain string in the input buffer by a certain ratio. And if this ratio is above a threshold, you can actually qualify that as a match. So in this particular example, I am using a string H with a small t and capital TP. Now this will match the HTTP version number in the HTTP PCAP, but the match is not exact. It is not 100% equivalent. So if you use normal string matching algorithms, you won't find a match. But in this case, you find a match because the match ratio is 75% and the default defined threshold in flow inspect is 75%. So if ratio is greater or equals to threshold, you will find a match. The match will be qualified. Even though there is no exact matching, you still have a match. Now this fuzzy string matching would be really useful in those cases where you have, you are working on a malware. You are working to identify a malware family, and a particular malware family has a known characteristic. So instead of writing, individual signatures for each of the malwares that belong to that family, you can write just one signature and match all of the malwares or all of the samples of that particular malware family. So one signature could match all of them because they are relatively equal. Although they are not exactly equal, they are relatively equal. So this is really important. Fuzzy string matching would be really important in such cases. This is just another example. I'm using a string H with small tt's and p. Now in this case, the match ratio drops from 75 to 50, and since we have a threshold of 75, there is no match. You can actually override the default of 75. There is a CLI for that. If you do that, you will find a match. That is obvious. Okay, let's move to Yara. Yara is the third inspection mode that Flow Inspect supports. Yara is basically a malware identification and classification tool. So Yara has its own rule definition language. You can write rules in a Yara format. There are Yara rule files, and then you can use Yara pass the rule files as argument and test certain local files or remote files to test for malware infection. So people, they write malware signatures using Yara's own rule definition language. And I have integrated Yara into Flow Inspect. So now you can actually use Yara rules to inspect network flows as well. Instead of just files, you can now inspect network flows as well using Yara rules. So in this particular case, I am not using a malware rule. Here, for example, I will show you that in the demo. Here I have a TCP rule. Yara rules. Let me show you a rule first of all. So here is an example of a Yara rule. So you see the name, definition, rule and the name, and in the bracket, in the parentheses, you see curly braces, you see the meta info, the strings that should be matched. So this is actually a signature to identify a certain object. In this case, this is a UPX encoded binary. If a binary is encoded or packed with UPX, you can use this particular signature to identify that. And in my case, I am using a TCP Yara rule, which will actually match on any HTTP traffic that has 1.1 or 1.0 in its version number. So rules are really simple. They just specify certain strings or hex patterns that are to be matched on network input or file input, and they have a condition defined down below. Whatever rules or strings you are defined, what should be the condition? So these strings should be matched all together, or they should have a ORing between them likewise. So coming back to the demo, here in this case I am using the TCP rules.yara file, the file here on the HTTP PCAP, and since it matches, this is HTTP PCAP, it has version number in it, version number is 1.1, and the rule will match on all 1.1 and 1.0 traffic. So in this case, you find a match, you have match statistics, offset, where exactly the match starts, where it stops. In this case, it's 19 to 27, matches of size 8 bytes, and it spans packet 1 and 1. That is, it is contained entirely within packet 1 itself. Let's move forward. Let's talk about shellcode. Shellcode detection mode. Now here, this is one of the best features that I think FlowInspect has. It uses a library called libemu. Libemu has Python wrappers as well. libemu is a library that you can use that can actually emulate x86 architecture. So it has a VM, it takes network traffic, or it takes binary data as input. Now this particular blob of data would be emulated in a x86 VM, and if the emulation is successful, it will actually tell you that these are certain shellcode patterns. There are shellcode patterns contained within. So there is also a getPC heuristics built into it. GetPC is something that shellcodes, most of the times they use that, because if you have worked with shellcode writing earlier, you will know that shellcode is basically self-modifying code, or it requires it is basically a platform independent or position independent code. So by that I mean, wherever you load it in the memory, it should be able to execute itself. So it has certain getPC heuristics built into it. So libemu has features to identify those getPC patterns, getPC blobs of instructions. So if it finds those instructions, it will tag that particular blob of data as shellcode, and it will tell you that this particular blob of data has shellcode and starts from this offset and ends here. So in this example, I am using a PCAP that has shellcode in it. I use Metasploit to generate a shellcode, and I took a PCAP for that, and I am testing it with FlowInspect here. FlowInspect tells me that there is a match on STC. Match starts at offset 104, and matches of size 174 bytes. So you have a 174 byte of binary data that actually corresponds to a certain shellcode. Now FlowInspect will tell you that it starts at offset 104. So within the entire input stream, at 104th offset, shellcode starts. Now from here, whatever next bytes are coming, they are shellcode. Now this particular info is good in a sense, but it is not exactly enough. You would like to know what exact shellcode is present in this particular stream. What exactly can this shellcode do once it is deployed on the victim system? What harm can it cause to the victim system? So this is where the profiling feature of libemu comes into picture. So libemu has a feature via which it can actually hook up certain Windows 32 API calls, and if the shellcode is trying to call those API, if it is trying to raise calls for those functions, system calls, it will trace them, trace the parameters that were passed to the system calls and the return values that were returned from the system calls. So if you request, there is a feature in FlowInspect. If you request it on the CLI, FlowInspect will also generate that profiling output for you. So in this particular case, even though I know there is shellcode in the network stream, I am not aware of the exact nature of the shellcode. What harm can it cause to the victim system? So I would like to profile that particular shellcode once it is detected. So I am using another CLI flag. There is a flag for that to generate profile output, and the profile output looks something like this. Okay, I'll show this output in the demo as well. For now, I'm not sure if you can see this, but it shows the load library A system call. So load library A is one of the calls, Windows 32 API calls, that is used to load certain dynamic libraries at runtime. So in this case, the argument that was passed was WS232. Here you can see it, WS232. So this is the Windows socket API, Windows 32-bit socket API. So this shellcode will actually try to load Windows 32 socket API. First of all, it will actually initialize the socket. This is a TCP socket being created here. You can see the WSA socket AF and type values here. There is a connect system call being made, and connect system call is actually you pass a sock addr underscore in structure. If you have used socket program, you will know that you pass port and the host IP or the host name using this particular structure. So here the port number is 4444, TCP 4444, and the IP is 192.168. You can see it here. And looking at just these 3 or 4 system calls and the values that were passed to these system calls, I am pretty sure that this particular shellcode is a reverse TCP connection. It is actually trying to spawn a reverse TCP connection. How is that? Attacker is actually sending this shellcode to a victim system. Once executed on the victim system, a socket would be created and a reverse connection would be. You are seeing the connect call. So this is a TCP for a TCP client server socket communication, this is the client part. Client is actually connecting to a remote end, and the remote ends are 192.168 the IP here, and the port number 4444. So now you know the attacker has a listening component open up on this particular port, on port 4444. He is waiting for a connection on this particular IP, and all of this information was extracted only from the first 174 bytes of the network data that you had. Only from 174 bytes of data, now you know where exactly the attacker is, where is the shellcode, where exactly the connection would be returned to, and what exact type of shellcode it is. Here are the details. This is a reverse TCP shellcode. Okay, let's have some examples here, real-world demos. So I have a number of demos set up here. Let's start with a vulnerability first of all. Now there was an issue. There was Stack Overflow in Adobe Reader, and it had a CV of 2009-0927. You can look up the CV page. Here it is. It was a stack buffer overflow in Adobe Reader, and there are a number of other portals wherein you can read about this issue. But specifically, let's focus on the Metasploit module for this issue. Here is the Metasploit module. It will actually create a PDF file. It is using JavaScript key sprays. It will embed it into the PDF file, and now once this PDF file, if you open it via the vulnerable versions, you will have a crash or you will get the remote shell. Now I have generated a PDF for this particular exploit, and I am using it as example here. Okay, so can you see the CLI? Is it visible? Okay. So here in this example, I am using a PCAP file, CV2009 download exec pdf.pcap. Now this PCAP has the PDF being downloaded, captured into it. So the entire PCAP is within, the entire PDF file is present within PCAP. I am inspecting it with FlowInspect. I have come up with a regular expression, the -s and the hex patterns you see here. The patterns don't really matter. What I am trying to show here is whatever signature, whatever pattern you come up with, FlowInspect will be really helpful as a tool to to give you some perspective into how exactly the match will happen and where will it happen. So in this case, I have come up with this particular regular expression to match only this PDF file. So if an exploit is happening, I will use this expression, use these hex bytes to identify this particular CV or the exploit that is being or the exploit that is happening through Metasploit. And I am using FlowInspect to check if it can actually help me identify these issues. FlowInspect tells me that this expression matches the PCAP file, and the match happened on STC direction. Here you see that match happened on STC direction. Match started at 7k bytes inside the stream. So match started at offset 7192. This in bytes, so it is 7k bytes inside the stream, and it is a 16-byte match. Now here is the important detail. Match spans packet 6 and 7. So even though you have just one expression, in this particular case, the data that you are trying to match upon is splitted across multiple packets. So in this case, FlowInspect is, FlowInspect can identify that this match, although it spans multiple packets, it is actually a valid match. So in case of NDEV, you won't be able to find such matches because it is splitted across multiple packets. It spans many packets. So in this case, entire content of multiple packets would be taken together, reassembled, and a single buffer would be created. So this buffer would be inspected upon. So the size of that buffer was some 8,000 or 7,000 bytes. In that case, we found a match starting at 7k bytes. Starting from there, the next 16 bytes match the input string, and it spans packets 6 and 7. It also tells you there are a number of other details down below. If you see, these are the global statistics, the ones that you see here. These are the global statistics. So if UDP streams are inspected, the count will be shown here. How many streams were processed or inspected, how many matches were found, what was the shortest and the longest match. In this case, for TCP, only one stream was processed, one match was found, and since there was only one processed and matched, the longest and shortest would be same. So you have a 16-byte match there. Alright, so let's move to the second example. I don't know if you have heard about UPX, but let me tell you something about UPX. UPX is primarily a packer, and packers are used initially packers were used to reduce to compress binaries, but then hackers, they started using packers to compress them or to evade some kind of detection mechanisms like IPS devices or AVs. So UPX is one of the packer that actually packs binary, and most of the time it happens that many malware writers, they use UPX as the dominant, it is one of the most widely used packers by malware writers. So if you have a binary that is packed with UPX, how exactly can FluentSpec help you to identify that binary? So in this particular case, first of all, we will test the negative part. We will test a binary. I have a malware sample here with me. I got this malware sample from, you can look for a malware sample anywhere on the internet. I found this somewhere, and this is a malware sample. I am testing it with UPX packer, first of all, if it is packed or not, just to show you that this is actually not packed. So if you see here, this is not packed by UPS. Now I have a PCAP for this particular binary, unpacked binary. I will test it with FluentSpec using the Yara inspection mode, and Yara will actually need a rule as well. So in this particular case, I am using the upx.yara rule. Let me show you the rule again. This was the rule that we saw earlier. This is the rule that I am trying to match upon a packed UPX binary. And these are the binary strings that we are actually trying to find inside the packed UPX binary. So if these binary strings are present, the condition is $0. If the $0 string, if this string in its entirety is present in the input pattern network stream or file, a match would be triggered. So in this particular case, since the binary is not packed with UPX, this particular signature, this particular test should fail. So you see here, there was no match found. If you see the match counts here, they are both 0. One stream was processed on TCP side, but there was no match, since the binary is not packed with UPX. Okay, now let's test the same binary. I have a UPX equivalent of the same binary. I have packed it with UPX. I am testing it again just for the sake of demo. Here it tells me, it identified it as UPX binary. It tells that tested one file and it is okay. It is packed with UPX. So I have a PCAP for this UPX binary as well. Earlier it was an unpacked UPX binary PCAP. Now this is a packed UPX binary PCAP. Now I will be testing that with FluentSpec. So I am using the same rule again. I am using the same UPX rule. Earlier it didn't match because it was not packed with UPX. So there was no, the particular $0 string, the hex bytes were not present in the input file. Now in this case, probably the pattern is there, and obviously, yeah, it is there, and you find a match. So FluentSpec tells you that inside that UPX packed binary, match happened on STC direction because I was actually downloading the file. So I sent a request, and the file was, there was a server that actually served the file to me. So the file was coming from a server towards the client. So this match happened on the STC direction. The direction doesn't really matter in this particular example, but the important details are the match starts at offset 12,000,120,954. So this is almost 120 KB inside the input file. So whatever the size of the input file might be, after 120 bytes, so at 120K bytes inside the stream, the UPX packed binary starts, or the pattern that you have used, it starts. And the match is of size 39 bytes. It spans packet 102 to 102. So this is just a one packet match, although it is very deep inside the stream, 100 packets inside this stream, or 120K bytes inside this stream. Alright, let's have another example. Okay, this one. So we'll be testing we have the shellcode detection mode as well. So let's test the first example, the first PCAP that we saw earlier here, the CV 2009-0927 PCAP. It is a PDF file. It has JavaScript embedded into it, and I am now testing it with shellcode detection mode. So there is no shellcode in it, but still I am trying to see what can shellcode mode tell me about that particular PCAP. There was no match. There was nothing. There are verbose flags as well. So FluentSpec has an incremental verbose mode. It supports 0 to 4. These are the maximum supported modes. So each of these mode will enable certain debug output from certain FluentSpec modules. So 4 is the maximum that you can have. Let's try with 2. So if you see carefully, for each of the packet, it will reassemble the stream and inspect all of them via the shellcode emulation feature. And if a match is found, it would stop there. It would show me the match. If a match is not found, it would move on to the next packet, reassemble the streams, create a new buffer and start inspection again. So in this case, for all of the packets, there was no shellcode match happening there. Does not contain shellcode, it tells me every time. So finally you see, one TCP stream was processed and there was no match there. Alright, let's test a shellcode PCAP. I have a PCAP, the one that I showed earlier, similar to that. This is a different shellcode. So if you see carefully, there were a number of bytes that were down. The match size is actually 359 bytes, so the screen scrolled up. So I will probably reduce the match size here. The output display size, I am displaying just first 32 bytes here. Even though the match size is 359 bytes, to read the meta info, I am just filtering it to first 32 bytes. So in this case, you see that shellcode was found in this particular PCAP. This is shellcode 2.pcap, and at this moment, I know that inside this particular PCAP, starting at offset 135, there is some shellcode in it. Okay, the size of the shellcode is 359 bytes. The count you see here, and it is contained entirely within packet 1 and 1. Okay, now I would like to profile this particular shellcode. I would like to know what exactly can this shellcode do, like we did in the example, the CLI usage that I showed earlier. So there is a flag for that. First of all, let me show you. There are no files here. Profile output files are not here, and you will see them once they are created. I will use the -y CLI. Output is exactly the same. Only difference is you see a file created here, TCP and some number. This is the TCP file tuple and the stream ID, and the extension is .env profile. Okay, this is the profile output that will be created if you request it using the -y CLI. Now let's have a look at the TCP profile output. In this case, you see load library system call is made again, like we saw in the example earlier. Windows 32-bit socket API is being loaded. Socket connection is being made. This time you see there is a bind call here. Okay, earlier there was a connect call. Now here we see a bind call. Then we see a listen call. If you see carefully, for the bind call there are port numbers, and the host is 0.0.000. Basically that means local host, and you are passing the bind call has some port numbers, has a port number as well. And if you are aware of TCP IP client server programming, you will know that bind and listen socket calls or system calls are made when you want to open up a local port to be connected by the client. So this is the server end of the TCP communication channel. So in this particular case, this shellcode is actually trying, if it is executed, if it is deployed on the victim, it will open up first of all load the Windows 32 socket API, and then open up a client server, the server end of the client server communication channel, and it will do that on local port 32303. Now in this particular case, once the victim is infected, port 32303 will have an open connection on it. So the attacker can connect to this particular remote port and gain access to the remote system. So now you know, looking at the profile output, that what exactly will happen once this shellcode reaches the target and it is exploited or it is executed there. There are a few other, let's have a look at this particular example. In this case, you will see a very this is also a shellcode that I found somewhere, and this particular shellcode will actually pop the calculator. You might have seen buffer overflows and stack overflow videos. They are spread across the internet, and most of the times it happens that people actually use a shellcode that spawns calculator instead of opening up a TCP channel on the victim, a reverse channel or a bind connection. They will actually pop up a calculator on the remote or the victim system to show that actually some kind of code execution is possible. So in this particular case, such a shellcode could be used, and even though there is some shellcode present in the network stream, looking at the profile output, you can actually infer the intent. Even if this particular kind of shellcode was deployed on the victim successfully, it would have not caused much harm to the victim. In this particular case, it would have just popped up a calculator binary. That is the worst that it can do. Okay, let's talk about future goals. Right now there are a number of inspection modes, but there are certain features that are missing currently. Primary features that are missing are, L7 inspection. So currently FlowInspect is unaware of L7. It is whatever it is doing on L4 payload. So it would be really awesome if we can have some STDP or SNDP POP3 decoding features in FlowInspect. Using those features, I could actually inspect upon or focus upon STDP payloads or SMTP payloads, the files that are transferred via emails, the attachments. And if we can have that particular decoding feature, we could have file extraction feature as well. We can extract files out of network stream. So if a file is being transferred over HTTP, I can extract HTTP payload, extract the file out, and I can use MD5 hash-based matching as well. So for example, if you have a malware thread going on and you don't have a Yara rule to match or to identify that malware, or you don't know the exact hex patterns to match that malware, in that case, the only info that you have is an MD5 or a SHA hash. In that case, if you have file extraction feature, FlowInspect will extract all the binaries in the network, take a hash of those files and match the input hash with those files hashes. So in case a match is found, you now know, even though you didn't have a Yara rule, you still find a match because the MD5 actually matches. JavaScript deobfuscation is that could be added. Most of the time it happens that recent exploits that use JavaScript obfuscation, all of the exploits are heavily obfuscated, and it is really difficult to actually infer the intent of those scripts. So it would be really awesome if we can have some kind of deobfuscation backend. And SpiderMonkey and V8 are some projects that I am looking at. SpiderMonkey is a JavaScript backend that Mozilla Firefox, the Mozilla project uses. V8 is the JavaScript backend that Chrome project uses. So if there are any issues specific to Mozilla, the SpiderMonkey backend could be used, JavaScript backend. Or if there are certain issues specific to Chrome, the V8 backend could be used. If these features are down the line, if they are integrated into FlowInspect. File format characterization. Now this is also really important. Some kind of anomaly detection for basic file formats that are normally used for exploitation, like jar and PDF files. So if I have file extraction, I can actually test for the validity of the jar file or the validity of the PDF file. So I can have a parser that decodes the PDF file and test if the file actually complies with the PDF standards. Okay, PDF DOM standards, XML standards. Integration with online scanners would also be awesome. If we can extract files, we can inspect them manually, or request a second opinion using online scanners. VirusTotal, Webpabyte, you might have used them already. These are well-proven solutions, so we can have a second opinion. We can submit our files to them, take their report and analyze that report to have a better idea of what exactly the malware is capable of doing. And these are some of the features that I have in my mind right now. I will be working upon them. The tool is already open source. It is hosted on GitHub. It is under CC license, Creative Commons license. And any new ideas, suggestions, or bug fixes are all equally welcome. You can submit your patches if you would like, or you can suggest new ideas. You can update it to to-do list. There is an issues list as well. I am working on that. Let's move to the credits part. First of all, I would like to thank the Python community, because they are the one who actually gave us the the awesome Python programming front end, and it is one of the best languages that anyone can use. Okay, it is arguably the best language that can be used for such rapid POC tools development. And in my opinion, I have been working with C and C++ earlier, but Python is the best thing that could have ever have happened to the security community. There are other projects like libnids, PyNids, Fuzzy Wuzzy, Yara, libemu, PyLibEmu. I'm thankful to the authors of these projects, because FlowInspect actually uses these projects, and if they were not there, FlowInspect would not have been possible, or it would have been really difficult for me to come up with such a tool in a really short span of time. And thanks to these projects, the authors of these projects, if you like anything about FlowInspect, you should be thanking the authors of these projects. I would like to thank the FOSS community in general, because they provide us an open culture. You can actually have a look at the open source tools. There are a number of tools released in conferences throughout the world, and you can actually have a look at the code. You can see how exactly people are trying to solve a particular problem, and you can learn from that. You can evolve these solutions. So it is a really good thing. I would like to thank Juniper Networks as well. They are my employer, and they allowed me to work on a personal project like FlowInspect, and they allowed me the liberty to work in code FlowInspect in my work hours as well. actually my teammates, they were the one who actually gave me the idea of working on such a tool that could actually, inspect network streams. Instead of just inspecting network packets individually, some tool should be there that could actually inspect network streams. So at the time we were not aware of FlowGrep, we were just using ngrep. Ngrep had this flaw wherein I would say it had a missing feature. It cannot match regular expressions over reassembled TCP data. So this was one of the missing features, and we started working on a tool that could actually cover this gap. And we finally encountered FlowGrep. FlowGrep had some other limitations, and we eventually added many other features into FlowGrep and came up with our own solution. FlowGrep is also a Python-based POC tool, and then we thought of implementing a tool completely from scratch on our own with our own architecture. So that would be all from my side. Thanks.